Hello, this is Tyler Beamer, Haywood Community College. This is an instructional math video for Math 172. This video is in regards to Chapter 5, Section 4, where we start looking at periodic functions. So we have already discussed how to evaluate and write ratios of the 6 trigonometric functions using right triangle trigonometry, and so what we want to talk about today is putting that on a rectangular coordinate system, and we do so using the unit circle. The unit circle has a radius of 1, so remember the center of this unit circle is going to be at the origin, 0, 0, and the length of the radius is 1. And so the equation of the unit circle is going to be x squared plus y squared equals 1. Since the center is 0, 0, and radius is 1, that is the equation following the equation of a circle. Okay. Another nice important thing to recognize is that the length of the intercepted arc to the central angle of a unit circle are equivalent. So here is the equation for the intercepted arc length, and since the radius is equal to 1, then the arc length, the intercepted arc length, to the central angle is equal to that angle. So let's zoom in just a little bit here. So we've got two examples here, one with positive angle and one with negative angle on the unit circle. So this is an example with positive angle where the angle opens counterclockwise. Okay, and so you can see the angle T is equal to the intercepted arc. Okay, here's the equation of that unit circle, and then this is where we try to show the relationship between the trigonometric functions and the rectangular coordinate system, where the terminal side of the angle and the unit circle intersect is a point P, which we give ordered pairs x and y. You can see we could also have angles that open in the negative direction where they open clockwise, so they move in this direction as well. So let's look at the relationship between this coordinate plane system, the unit circle, and the right triangle trig that we have been studying. So let me get some workspace over here. So notice that I could drop a perpendicular from the point P down to the x-axis in either of these scenarios, whether the angle is positive or negative. Okay, and so that's going to create a right triangle, something like this. Here's the angle measure, the central angle, okay, of the unit circle. We know that the radius of the circle is 1, and so that is the hypotenuse of this right triangle. And I know that this is the side opposite the central angle, right? And this opposite side gives me the vertical distance from the origin to the point P. So this is actually describing the y coordinate of point P. This is the adjacent side to the angle. This adjacent side is giving me the horizontal location from the origin to the point P. So this is actually giving me the x coordinate. Okay, and then we know that sine of the angle is equal to opposite, which is y, over hypotenuse, which is 1. So then the sine of our central angle is equal to the y coordinate of this point. And then I know that cosine of the angle is equal to adjacent over hypotenuse, and adjacent side to the central angle is x over hypotenuse, once again, which is 1. So then I know that the x coordinate of this point is cosine. So essentially the point P that's on the unit circle gives me the sine and cosine of that central angle. So P is going to give me cosine of the central angle and sine of the central angle. And if I have sine and cosine, then I can divide sine divided by cosine to get tangent. And then of course, if I have the first three trig functions, sine, cosine, and tangent, then I can use their reciprocals to find cosecant, secant, and cotangent. And so that's what is being described here in this definition. So the unit circle is pretty helpful, okay, because it's a handy-dandy way for us to evaluate trig functions at those specified angles along the unit circle. And we actually completed the unit circle the last time that we met. And so this is what the completed unit circle looks like. And so what we did is we actually took the started with a 45, 45, 90 degree right triangle. And so we used that to find the value of sine, cosine, and tangent of 45 degree angles. And then we looked at an equilateral triangle where we had three angle measures of 60. And then we divided that equilateral triangle into two right triangles by dropping a perpendicular bisector to create two 30, 60, 90 degree right triangles. And so then we did our right triangle trigonometry to find the value of sine, cosine, and tangent for both 30 and 60. And so we used those piece of information to then go through the unit circle and find the x and y coordinates for all of these central angle measures. And so you've got the central angle measures in degrees, also in radians, and then the x and y coordinates at each of those points. And then we use the idea that the unit circle has radius of 1 to find the values at 90, 180, 270, and 360. So, some things that you can do with that unit circle is you can evaluate pretty much any trig function. If we have angle values that correspond to what's on the unit circle. So let's look at it. Determining the value of tangent of 5 pi over 3. So if we look at our unit circle, right, we know that 5 pi over 3 is here. That's equivalent to 300 degrees. So I know that the sine of 5 pi over 3 is negative root 3 over 2, and the cosine of 5 pi over 3 is 1/2. Okay, so I'm going to write down that information. And that's coming from the unit circle that we created. And so then if I want to find tangent, I just do sine divided by cosine. So then the tangent of 5 pi over 3 is going to be equal to negative root 3 over 2 divided by 1/2, which is going to be equivalent to negative root 3. And so that's the value of the tangent of 5 pi over 3. So we used our unit circle values to come up with that. We could also do the same with a negative angle measure. So find positive 11 pi over 6. So if we went this direction, that would be positive 11 pi over 6. So if I go clockwise, that would be the negative direction. So go in this direction. So we know that positive 30 and negative 11 pi over 6 are coterminal angles. And so then I can use that idea to solve for the tangent, negative 11 pi over 6. I know that the sine of negative 11 pi over 6 coming from my unit circle is going to be equal to a half. And I know that the cosine of negative 11 pi over 6 is equal to root 3 over 2. So then if I do sine over cosine, I can solve for tangent. Which is going to give me 1 over root 3. And so then if I rationalize that denominator, I get root 3 over 3 positive. Okay. Domain and range of sine and cosine. The domain is going to be the angle value of the central angle here on this unit circle, and so that actually goes from negative infinity to positive infinity. Remember that I can make as many rotations around this unit circle as I want to increase the angle value. So depending on the direction, makes the angle either positive or negative. And the range is going to be the actual value of those trig functions at those angles. And so notice that basically I'm just going to continue to go through the unit circle a number of rotations. And so things are going to start to just be cyclical. And notice that all of these values on this unit circle, all of these x and y coordinates, are all between negative 1 and positive 1, inclusive, which means that we actually do have values of positive 1 and negative 1. Okay, and so that is the range of those sine and cosine functions. Okay, even and odd trig functions. Basically, we're seeing what happens to the value of the function if I change the sign of the angle. So if I make the angle measure negative on cosine and secant, notice that the value of that trig function does not change if the angle was positive. And so let's take a look at the unit circle here. I know that the cosine of positive 30 is root 3 over 2. Well, the cosine of negative 30 is still positive root 3 over 2. And so we can see that that continues to happen as I move through the unit circle. And so we call that an even function. And then for sine, tangent, cosecant, and cotangent, we call those functions odd because what happens is the sine of the negative angle is actually the negative value of the sine of the positive angle. So let's take a look at that. Let's say sine of positive 30 is 1/2, right? So the sine of negative 30, which would be the 330 here, is negative 1/2, right? So it's basically the same number, right? But the sign changes. And that's what we call a odd function. And so that's what this definition is describing. And so that's a helpful understanding, kind of a shortcut when evaluating trig functions. So let's look at the cosine of negative pi over 6. So here is pi over 6, which is 1/2. So since cosine's an even function, or I'm sorry, root 3 over 2. And so since cosine is an even function, then the cosine of negative pi over 6 should be the same. And we could see on the unit circle it is. Okay. If I move negative pi over 6, that's the same as 11 pi over 6. And notice that that cosine value is still root 3 over 2. Okay. Alright, and then we get into this notion of periodic functions, which we're going to spend a lot of time looking at. When you think of something that is a periodic function, think about something that is cyclical. So the book gives a good example of tides. So if you've ever been to the coast, you can see that tides come in and out on a cyclical nature every 12 hours. And so the tides go from high to low, low to high, and it just repeats itself. So that's an example of something that's periodic. If I look at sine and cosine on my unit circle, right, this is also cyclical in nature. Right? As I go through the central angles 0 to 2 pi, right, I get the values of sine or cosine based on the coordinates that I'm looking at. Okay? And then if I have angle measures that are greater than 2 pi, basically because those angles will be coterminal, they have the same values of sine and cosine, and so these values just repeat itself over and over and over again, depending on how many rotations you go through the unit circle. Okay? And so that's why cosine and sine are periodic functions, and they have a period of 2 pi. Right? And so that's what this definition is describing. Basically adding some value and getting the same result. So if I look at my unit circle, if I'm at 30 degrees, the cosine of 30 is root 3 over 2. Well, if I add 360 to that, right, then I'm now at 390, which is still coterminal with the 30-degree angle, and so the sine or cosine of 390 is still root 3 over 2. Right? So everything is still cyclical. Okay. And so you can use that idea, notion of periods, to solve or find trig functions that are greater than 2 pi. So I know that 11 pi over 4 is greater than 2 pi. I definitely make one rotation through there. So I'm going to subtract 2 pi from that to find an angle measure that is coterminal to 11 pi over 4, and that angle measures 3 pi over 4. And so if I look at 3 pi over 4, right, and I look at the sine of that, I get root 2 over 2. Okay. Cosine of 9 pi over 2, right? In this case, I'm making 2 rotations, or more than 2 rotations. So basically, I'm going to subtract 4 pi from 9 pi over 2, right? And that's going to give me pi over 2, and so that is, once again, the coterminal angle. So pi over 2 and 9 pi over 2 end at the same place, right? So that allows me to then find the value of the cosine of 9 pi over 2, which in this case would be 0. Just going to include these notes just to try to be a little more clear as to where those values are coming from. Okay. And I will scan these notes into Moodle so you'll have a copy. Alright, and then if we look at the period for tangent, the period for tangent is actually pi. And if you can look at your unit circle, you can start to see where tangent starts to repeat itself. You know, if I look at these ordered pairs in the first quadrant, notice they're both positive, positive. And I get tangent once again by doing sine over cosine. And then if I go 180 over, so directly across, notice I got the same numerical values except these are both negative. Well, negative divided by negative is still a positive, right? So the tangent of pi over 4 is equal to 1. Tangent of 5 pi over 4 is equal to 1 as well. Okay, So tangent becomes cyclical after a half of a rotation, and same thing for cotangent. Okay. So we can use that information to evaluate trig functions for tangent and cotangent. Okay, so if I look at tangent of 17 over pi, right, I know that basically 16 pi would be 8 rotations, and then 17 pi would be this half rotation, which would put me at pi. And of course, tangent is sine divided by cosine, so that's 0 divided by -1. So basically, the tangent of pi is equal to the tangent of 17 pi, since they are coterminal angles there. And so you get tangent of pi is equal to 0 divided by -1, which is 0. Okay. Cotangent, so if I look at 15 pi over 2, right, I know that I'm at least doing 7 pi rotations, so that I'm going to do 15 pi over 2 minus 7 pi to find the coterminal angle there, and so that's pi over 2. So one thing to keep in mind here is that when I do 7 pi rotations, right, I'm basically doing 3 full rotations and then another half rotation, okay, which would put me here. And then if I do pi over 2, that's another quarter of a rotation, which is going to put me here at 3 pi over 2. And so I know that cotangent of 3 pi over 2 and 15 pi over 2 are coterminal. And so cotangent of 3 pi over 2 is going to be cosine over sine. So 0 divided by -1, which once again is equal to 0. Okay. So hopefully this video will help with instruction on this section. If you have any questions whatsoever, please email those to me, and have a great day.